m lambda, but what in that equation can actually change? And in that equation, for our case, only the lambda can change, and that will influence our angle theta. Okay? How do we feel about that one? That is probably like one of the weirder problems that exists in this unit. Going into fish land.
It makes sense.
I
I
was very
assumed
unsure at the beginning, but now I feel good about it.
that like it's just like we have a wall underneath the water, and then we just have a light source that's like all that is also underneath the water. So like the lambda changed between the air and the water, but when it's underneath the water, it just remains the same.
So when that light is underneath the water, it is going to be slow to begin with. Even though the light's not going to like refract being in the water and staying in the water, it is going to be slower down there. It is going to be slower. There's actually something, and we'll talk about it briefly later on in the year, and we're going to talk about it briefly at the moment. There's something known as Cherenkov radiation, Cherenkov, Cherenkov, where when a neutrino hits, like, I think it's like when a neutrino hits something in the water, it essentially gives off blue light. And what actually ends up happening is the neutrino is moving like faster in the water than light can move in the water. So like the neutrino is moving faster than light. It's not moving faster than light. It's moving faster than light is able to move in the water. And by doing so, it releases like a blue light. And we can detect the blue light, and that allows us to see neutrinos, which are really hard to see. But yeah, it's just a matter of being in the water forces a different speed of that light due to this equation right here. And we're going to use this equation later on in this unit when we get into thin films in a few days.
Wait, so having like a denser atmosphere, does that like allow you to have could that change like the way that light is traveling? Like if we go to just a faraway planet that has a super dense atmosphere, will the lambda change for that atmosphere? Like compare,
Yes.
because I imagine like if you have like all water or all air, it will change.
Yes. It might not change a lot though. So one of the things is that a perfect vacuum has an n value of 1, and for the index of refraction, and the index of refraction of air, it's like 1.01, right? So at least through our atmosphere, it's 1.01. So if you have a thicker atmosphere, your index of refraction will still be very close to like 1.01. What will change is what's referred to as your optical throughput, also known as a optical depth. And think of it this way. You know how some days you can like kind of see a little bit through the fog, and then some days you can't see through the fog at all? Well, that fog is still just water vapor, right? So what's really happening there is there's more particles that are absorbing your light, so your light doesn't get as far. There is a difference between slowing the light down because you have some index of refraction and just saying, I have built a wall in your way that is absorbing all your light rays. Okay, if that kind of makes sense. Like, how do I describe this? Most of the glass that is made nowadays is made very, very clear because we have gotten good at making glass. But old glass making processes, hundreds of years ago, they would make like dirty glass where the glass itself absorbed the light. It had like imperfections in the glass, like dust particles that would the light would hit and it would die there. Okay, so that's the idea of like an optical depth. It's like stuff is hitting and dying, and optical depth is different than an index of refraction. Does that kind of make sense there, Gio?
Yeah.
It's described to me in college as if you had a imagine a tube. Okay, these are identical tubes. They're both glass. Okay, but this tube here has a bunch of dust particles in it.
Mhm.
When you shine light through here, this light's still going to like bend and refract and do its thing, right? But all of this light is going to get through. It's perfect. Here, some of the light is going to get through, but some of it's going to hit this piece of dust and die out. And that's going to be it. End of the light. So that is the idea of an optical depth versus a index of refraction. Okay, so we don't really talk about optical depth in this class because it has no bearing as to the interference patterns that we're dealing with. I've got like a single hair in front of my face that I can't get rid of. This is the worst. But in like nuclear applications and stuff, it starts to have some meaning. Oh my goodness, this is my hair is betraying me. Someone help. Someone help, please. Did I get it? I can't even hear all of you laughing at me. Okay. That was ridiculous. I apologize. Stupid hair. I love it. Okay. Okay. Any other questions regarding the fish question and the double slit underwater? Okay. Let's move on then. Problem number 6. Faria Jerry, Christmas singer extraordinaire of the Intergalactic, is putting up a number of non-denominational holiday lights of the standard wavelength of 550 nanometers, which is green light. And it's because green reminds people of their favorite soylent-based foods. I don't know if you've seen that movie. But Faria Jerry then notices a coherent beam of light. So all the waves are in phase, which is very important. And it's passing through a small microphone cover, and it is diffracting to a bright point at an angle of 38 degrees. And all we want to know is what is the spacing of the speaker cover wires? So effectively what we have is we have a double slit, and what we have here from our center out is we have a nice angle here of 38 degrees of light of wavelength 550 nanometers. So if we want to solve this problem, this is actually very straightforward for us using a double slit. We can say d sine theta equals m lambda. This is our first bright point, so m equals 1. Our lambda is the color of the light, which is a lovely green, so 550 nanometers. And we know our angle in this case, 38 degrees. So this has got to be like the easiest math you've done all year because the year just started. So you can just say d equals m lambda over sine theta, right? That's it. That's the whole problem right there. And the really, really cool thing about this is since m is just an integer, it's unitless. So it's just a value of 1. Sine of theta, well, all functions, sine, cosine, tangent, all 3 of those functions at least, those are on the unit circle. These are all unitless. So the only units we actually have are on this lambda, this wavelength. So if we just keep our nanometers right here, then our answer will be in nanometers. So if we just take 1 times 550, so that's 550, and then divide it by sine of 38, we get a value of 893 point whatever nanometers. And that's it. That's the problem solved. I didn't even have to remember that nano is times 10 to the minus 9. I just say it's nanometers again, and I'm done. Okay. How do we feel about that? And just in terms of a quick double slit setup, solving for something like the speaker spacing D. Hands up if you like that, if you feel good about it. Hands, 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 hands. Hands. Okay, got a few hands, got a few no hands. Okay. Let's try this. In question 7, it's a slightly different setup. I'm going to put this question in all of the chats. There it is in there. Here it is in here. So I put it in both chats. And if you went blind over break for some reason, here it is in vocalizing. Overlord Restob is worried that his hair is thinning. Not that it's an issue, because he rinses and repeats. But in an effort to find the diameter of a single hair, it is placed in the path of a laser of wavelength 650 nanometers, so something just under red light. If the distance between the central maxima and the first bright fringe is 2.2 centimeters, and the distance of 190 centimeters to the viewing screen, what's the thickness of a single perfect hair? So I'll help you on this one part, and then I'll leave the rest to you. I'll give you a few minutes, and then we'll talk about this, because I want you to start kind of thinking about these problems and starting to work out these double slits that we did before break and kind of getting that all back to you. 'Cause it's all coming back to me. That's Celine Dion. Our central max will be something like that. And our first bright fringe will be somewhere else, right? What you know is that this distance here is 190 centimeters. You know that this, not drawn to scale, is 2.2 centimeters. This will allow you to find an angle. Try this one out. Try this one out. I'll put on let's put on some. Let's get this.
Hey, Mr. Botzer, should we convert the 650 nanometers to centimeters, or can we just plug it in as normal?
The what? The 650 nanometers?
Yeah.
Try leaving it. See what happens. See what happens. Because this music doesn't cause panic in all of us. This music is 10 hours long? Holy smokes. Bum bum. Okay, let's see what we're thinking of here. So someone walk me through what you're thinking and setting up this problem. What we thinking?
I got the equation, since we're finding the theta, I got it equals theta equals inverse sine of m times lambda over d.
So theta equals inverse sine of what? M lambda over d?
Yes.
And what do you have for m?
Would it be 2.2?
And what do you have for lambda?
This is 650 nanometers.
And what do you have for d?
190.
Let's see what our answer is. 2.2 times 650 divided by 190. Inverse sine that sucker. I got an error.
Wait, how did you put yours in the calculator? Because I got an actual answer, but I'm confused.
Well, I did 2.2 times 650, because that's the numerator. Then I divided by 190, and I got 7.52. Then I took the inverse sine of 7.52, which I know is impossible, because if I'm taking the inverse sine of something, it needs to be between -1 and 1. Ba, ba, ba. So something's here is messed up. Let's fix it.
Fuck off, come on.
Other thoughts to fix Aiden's equation or to modify it in some way? If you've got something, say something.
Convert, pardon. Convert nanometers to centimeters, the 650 nanometers.
That will come out to 6.5 to the -5.
So 2.2 times 6.5 times 10 to the -5 divided by 190. Inverse sine of that gives me essentially 0. Quick question. When I take this right here, what are the units of that inside parentheses? Is Geo talking? I can't tell if he's talking or not.
Oh, sorry, I was on my calculator.
What do we think there? Well, here, let's go the other way around. Let's do this the other way. If I have something like sine of an angle, right? That would equal m lambda over d. Well, that means sine of an angle equals something, right? What are the units here of sine of theta? If you take sine of some angle, what will the units turn out to be?
Degrees.
Degrees.
Degrees?
Yes.
Would it be radians?
I don't think so. Because can you do sine in radians?
Sure, why not? Sine of pi over 2 is 1, right? What have I drawn?
The unit circle.
There we go. Thank you, Mr. Ross. You're going up in that tier list.
Heck
And
yeah.
when I draw a vector in this unit circle, what I'm really drawing is I'm saying this is some cosine component of it, and this is some sine component, right? Well, what are my units of the unit circle itself?
The unit circles in radians.
Let me ask you this question. I have a board. It is 10 meters long. It is at an angle of 30 degrees as it leans up against the house. How tall is my house?
Is it 5 meters because of Pythagorean?
Not because of Pythagorean in this case, because you don't know what this side is. But it is 5. This is your opposite side here. This is your adjacent. This is your hypotenuse. And if we use a little bit of SOHCAHTOA, we'll see here that the sine of 30 degrees equals the opposite side, which we don't know, divided by the hypotenuse, 10 meters. When you get the height of this house, what will the units be in? Well, if I take 10 meters and I bring it over, this will be 10 meters multiplied by the sine of 30 degrees, which gives you 5 meters. So my question once again is, what are the units of sine?
They're in meters?
Well, if sine is in meters, then what you just did is you took meters multiplied by meters, and this should be meters squared then. But that doesn't make any sense because I asked for the height, not the area.
Sine's an operation, it's unitless.
Sine, cosine, and tangent are unitless functions. They have no units associated to them. They are simply there to scale vectors. That is their function. They scale other things. That is what they do. They are unitless in nature. This on the inside has to be in either degrees or radians. But remember, degrees and radians, those units don't have any physical meaning. They're made up hogwash. Because if I said, hey, I'd like you to run 360 degrees for me, you could do this in a number of ways. You could sit in your chair and just spin in a circle. And if you spun in one circle, I'd be like, okay, that's 360 degrees. Congratulations, you're a pretty fast runner. Or you could stand still for a year and go around the sun 360 degrees. Your circle has a much bigger length, right? You know, circumference equals 2 pi times the radius. 2 pi is the angle in radians. But angles have no physical meaning. They mean nothing in terms of units. Okay. This is also why last year, whenever you talked about circular motion, you started talking about that a linear velocity is equal to an angular velocity multiplied by some radial distance. And if we look at the units on this, this is like radians per second times meters. Nobody rates velocity as rad meters per second. Like, that's not a velocity. That makes no sense. What the heck is this radian doing here? Radians mean nothing on a physical sense. It's just an idea of how much you have rotated through something. Velocity is clearly meters per seconds, okay? So radians, degrees, they're not real units. They don't mean physically anything. So sine, cosine, tangent don't have units associated to them. And if we go back and we look at this problem with Freya, or with the hair, we need to ask ourselves, if sine of theta doesn't have any units, that means whatever is on the inside of this parentheses is not allowed to have any units either. That must be a unitless quantity. And if we look at the values Aiden has given me here, the 2.2 is in centimeters, it's a distance. The 650 is in nanometers, it's a distance. In the denominator, I'm in centimeters, it's a distance. So I have some centimeters, and then if I wanted to convert to centimeters, and then I could divide by centimeters, that's not unitless. I have a value there. So something in these numbers given to us is messed up. So let's try to figure out what that is. The weird thing about this type of problem is that what we're actually doing here is we're plucking off a strand of Reztov's hair, straightening it out, and then shining a laser at it. This space right here, this D, that is actually the width of the hair. That's the hair right there. This is what we are looking for in the problem. So I don't want to solve this theta here in this way. I'm trying to solve for D. So let's rewrite this equation then. Same equation, just rewritten, and say D equals m lambda over sine of theta. And let's try to go about solving that equation in green. So how would you go about doing it? What do we have in the problem? What don't we have in the problem? Shoot your shots. See what you get.
You would have to take the sine of both sides to get rid of the arc sine on the right.
Which arc sine?
Well, your inverse sine. Wait, are we just like deriving the equation, or?
No. We have this equation right here.
Oh.
Okay. This equation Aiden had would give us theta. But we see in doing so that we still have a unit here. And in this problem, the hair is actually what is splitting the light. So we're actually looking for D in this problem. That is the hair thickness. And if we're looking for D, we're using this equation down here. So how would we fill out that equation numerically?
So would it be 2 point? I don't know.
Go with your gut. Just say it. We'll see what happens. You got to try something. And you're the only person trying something, so we're going to count on you to either do it right or wrong. And it doesn't matter because either way, it'll give us information.
So wait, we're solving for D, correct?
You bet.
But we already know what it is, don't we?
What is it then?
190?
190 is how far away the hair is from the viewing screen. It's this big distance. If D was 190 centimeters, then that would mean that each one of my hairs had a thickness of about 6 feet. And that's a lot. It's a very luxurious head of hair.
So would it? So
Mr. Ross raised his hand. He put it down. Maybe it was a misclick. I don't know.
Do we need to solve for the angle first? By using Sokotoa?
Would you like to? How would you do that?
Sokotoa.
Regarding
Goes-
what?
What is it? Tangent. So if you
All right,
combine
when you
the
tell me to.
yeah, tangent, and that's what? Opposite over adjacent 2.2 over 190. And then calculator.
And I believe you don't mean tangent here, Mr. Ross. You mean something else very similar to tangent.
Is it cosine?
No.
Is it inverse tangent, I'm guessing?
There you go.
Alright. I'm sleepy. Go
When
to
you do this, we know this length up here between the central max and the first fringe, and we know this big length here. This allows us to get the angle using the inverse tangent, like Mr. Ross has pointed out. And since both of these are in the same units of centimeters, the centimeters go away and it's unitless, which is very nice. It'll give us some angle here. So, I don't know. Let's see. Calculator activate. Inverse tangent of 2.2 divided by 190. This angle is small. That's okay. It's just a number.
I got
an angle. I got 0.66 degrees.
Yeah, that's what I got.
Okay. So this angle we can shove into here. That was the only thing we needed this picture for. Now our questions become, what goes in for M and what goes in for lambda?
Lambda would be the 650, wouldn't it? And then M would be just 2.2.
If you have a distance multiplied by a distance, that'll give you some area, right? Which, that should just be a length here. This should just be a distance or a length. So both of these can't be distances. One of them could be. Actually, one of them must be. One of them has to be a distance. Which one has to be a distance then?
The wavelength?
Yeah, it's literally a wavelength, right? So this is our 650 nanometers. What is M then?
Or would it be just one?
Do we agree with that?
Why would it just be one?
Great question, Gio. Why would it just be one?
Because would it be because whenever it's like, since like between each of the peaks is 2.2, that would mean that Like it's not the distance between them is 2.2. That doesn't mean that, but M can be 1. I don't know how to describe it. I just feel like that's how it's gonna have to be.
Aiden's brain melted in trying to give you an answer, Geo, but he is right. It is going to be 1. The question is, why in the world is it going to be 1? Can we accurately explain what the heck is going on to make that value 1?
Is it because that's when the 2.2 only represents the distance between the two bright spots, not where the bright spots like where the bright spots are going to be? Like,
his brain's on fire, people. He's so close. Remember, what M represents is which fringe are we looking at? M equals 0 is this central fringe here. But then when we're 1 wavelength away, we have another bright point. And at 2 wavelengths away, we have a second bright point. It represents how many wavelengths away you are. It represents which fringe or which order number you are at. Since we went from the central fringe to the first bright fringe, M equals 1. That is it. If you went to the second bright fringe, M would equal 2. M must be an integer value. 1, 2, 3, 4, 5, 6. You get the idea. But it has to be some integer value. Okay? So in this case, for us, M will just be a value of 1. It is unitless, thank goodness, because now when we look at this, our answer will be in nanometers. And we can just take 650 divided by sine of 0.66 to get D. What we find here is that 650 divided by sine of 0.66 gives us, this is stupid, 56,428 nanometers, which is approximately 56 micrometers, which is a pretty good value of a thickness of a human head of hair. Okay. That is the double slit there. That is what is going on with our double slit equation. And that one was a little different because this time I didn't give you the angle. You had to use the actual apparatus dimensions and setup in order to find it. Normally that'd be a little easier for us because we'd do that in a lab, but global pandemic, how you've betrayed us. Okay. How are you? What are your questions regarding that question there? I know we covered a lot in it. And we kind of went on a tangent of what sine and cosine and tangent of tangents actually are. But how do we feel about that question there?
I'm feeling good now. I was doubtful pretty much the whole time, but after finishing it and getting to look at the whole thing, I'm pretty good. I'm pretty good with it.
yeah, like once you explained that, like when the theta had to be unitless, and every single time whatever number we plugged in, it wouldn't be unitless, it made more sense. I just didn't know that's the thing. It's like trying to figure out what M was going to be. I knew what it meant. I just didn't know how to describe what M is supposed to represent, and that makes so much sense. Like it's just what fringe, like the fringe order and stuff like that.
Yeah.
I didn't know how else. I didn't know how to describe that, but now that you point that out, it makes so much more sense.
Okay. Okay, so that was intergalactic question number 7 right here. To the left of that, this 893, this is intergalactic question number 6. This one was number 4 up here with Noah's brother in the bedroom and concrete walls. And the master fish Mon Calamari experiment was number 5. So we just did 4, 5, 6, and 7 together. Okay. There is another double slit equation. It looks very similar to d sine theta equals m lambda. It looks very similar to this, but it is not this equation. Does anybody remember what the other double slit equation is and what it does?
The other one's d sine theta, and then the quantity of m plus a half times lambda. And it tells us what our dark spots are going to be.
This finds you dark points, okay? With values of m being 1, 2, 3, 4, dot, dot, dot. M, excuse me. Why did I do that? I think I did this last time when I showed this to you. M equals 0, 1, 2, 3. M equals 0, 1, 2, 3, 4. And this is the case because if m equals 0, this is your central bright point. If m equals 0 here, you still get a half wavelength separation. Because when we look at these graphs, we will have the central peak so here's our central peak. And then here is lambda over 2. And here is lambda. Here is 3 lambda over 2. Here is 2 lambda. And symmetry on the left side. Okay. So these half wavelength shifts, these are where we find the dark regions. Okay. That is what we're finding in those dark regions there. It's a very similar equation, but there's a plus 1/2, and then it's still the m equals 0, 1, 2, 3, 4, blah, 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 for everything. Okay. But that is all that means. It's just which fringe are you at? How do I... Let me pause something real quick. I want to look at something. I feel like I'm writing this in a slightly different way than I did it in my notes last time. How did I write it for you last time? Because there's a million ways I could write that. I don't want to mess this up. How did I write it here? Yeah. Okay, great. Perfect. Perfect. Okay. Okay. Yeah. Okay. Only thing to slightly be careful about is this m equals 0 point right here. That is right there. Okay. It's like the first dark fringe is the 0th m value, because when you put in 0 into this equation, you still get a half out of it. So just recognize that when you draw your pictures, it really makes sense pretty quickly. But it's just something to be aware of there. Okay. How do we feel about this now in terms of the double slit? I know we like churned through a whole bunch of stuff pretty quickly, but it was kind of like a mega review of what we did before Santa came, or I don't know, whatever. How do we feel about all this? We feel a little bit better? Is it all coming back to us?
Yeah, it's coming back.
Yeah, it's
making
coming
sense.
back.
I forgot about the darkness, the 2 lambda. 2 over lambda.
Oh, darkness, my old friend.
I wish I could forget the
Okay.
darkness. I saw the chance and I had to take it, bots. I'm sorry.
At least you didn't just start trying to sing I believe in a thing called love. By the darkness. Okay. If you still have questions regarding some of this double slit stuff, please reach out to me. Shoot me an email. Try to I don't know what kind of free time that you have during the day, but I am on I'm sitting in this chair from about 7 a.m. until I'm done with you guys and lady. So if you've got a study hall or something during the day and I'm not teaching my CP class, which that might be where the study hall locks with you guys, and like try to reach out to me and I can help you out with stuff. What we are going to talk about tomorrow, and we only have 2 more things to discuss within the world of wave optics. We've been talking about a double slit here. What we're going to see tomorrow is what is referred to as a single slit. It is very, very similar to what we've been doing here. That's why we start with a double slit. But it has slight changes to it. And it's something that, like, when we start drawing it out, it starts to make more sense on the mathematical spectrum. But we'll start looking at a single slit tomorrow. Okay, so we've done the double slit. We need to talk about the single slit tomorrow. And then the last weird thing within the world of wave optics is the idea of thin film interference. Okay, thin film interference. That will be the last thing that we cover. The way things are going to pan out scheduling wise then is technically our semester ends on the 22nd, but we are going to end the semester with the completion of wave optics. Okay, so if we finish on the 13th next week, then that wave optics test, whenever it comes up, that's the last thing that's going on the first semester. Okay, whenever we take it, everything after that is going on to the second one. So we've got like 2 last things, and then our semester will kind of close out, and we'll be all set there. Okay. That being said, if you have old intergalactic stuff that you are still holding on to for some reason, please get that stuff to me and just submit it into the Canvas as soon as possible. It does take me some time to look at the intergalactics. They are more complicated problems than what I give to my CP classes. And I want to give you as much time to make corrections if you need them. Okay. Which I know the solutions are out there, but, like, people, if you still have old stuff and you haven't corrected it yet, you might need some time. So please try to get your old intergalactics into me by Monday, January 11th, like at the latest, because that'll give me a solid week and a day or two to get stuff ready for the end of the semester. And that way your scores will be in there. So if you're looking at your old stuff and you're like, oh boy, is he talking to me? Do I need to get stuff in? Yeah, I need to get stuff in. Give me what you've got. So I can get that graded and into the system. Okay. And make sure you take a photo of what we've done today, problems 4, 5, 6, and 7. I'm going to be putting up a little, like, turn in thing for that. 2 of us weren't here today, so that kind of stinks if you weren't here. Nate and other student I can't identify quickly. But yeah, make sure you're taking a snap of those, and I'll put a little something up so you can submit them. And that's it. That is it for today. Okay. Any other questions, comments, concerns before you all start abandoning this channel?
I'm just kind of curious for tomorrow about the single thing. The
Single slit.
single hole. Yeah, single slit.
It's going to be exciting. It's going to be exciting. But until then, I'm glad this all came back to you. Okay, bye everybody. We're listening to Celine Dion now. This is now a Celine Dion channel. We're gonna get
Wow.
DMRC'd or whatever it is
DMCA, baby.
by Celine Dion, my favorite Canadian singer.
Oh, my favorite spam risk from
Mine's
Outclass.
Anselmo Brache.
Have a good day, Mr. Botster.
Later.
Adios.
Oscar.
Take it easy, everybody.
Bye, bots.
I'm gonna be hopping out of the stream and immediately sleeping. I'll see you later, bots.
See you, Tom.
There were nights when the wind was so cold, my body frozen.